Okay, so what we've seen so far is the representation of systems. Systems are represented by models, typically ordinary differential equations, and these ordinary differential equations can be turned into transfer functions if we use the tool called Laplace transform. So these transfer functions, they are rational function in a dummy variable called S. This S belongs to C, the complex number. Can be seen as the input-output relation, the causal relation between what goes into the system, the signal that goes into the system, which we usually call U, and what goes out of the system. We have seen also in the last slides that if the input to the system is a pure sine of angular frequency omega, then the output is also a pure sine of angular frequency omega in the regime, okay, at the infinity, for t going to infinity, or at least let's say there exists a solution which is also a pure sine, to which in most cases all solutions converge if the input is a sine. And the interesting thing is that this sine of output, the y when u is a sine, we said is also sine of omega equal same omega, let's say, and also the amplitude and the phase shift of this sine can be derived very easily from the transfer function. Just take the modulus and the phase of the transfer function evaluated at j omega, which we also call sometimes the frequency response. So as we know from Fourier theory that all signals are a combination sum of harmonics of sine, this is very important because if you decompose any signal into the harmonics component, then knowing the value of h of j omega for each omega allows you to understand what you will have for output. Due to the linearity, if you give a certain input, which is the sum of certain harmonics, and for each of these harmonics you can compute which will be the output just by computing the modulus and argument of h of j omega, which omega corresponding to each angular frequency of each component of the input, then the output will be basically the sum of each harmonic amplified by the modulus of h and shifted by the phase of h, the argument of h. So that's why this guy over here, h of j omega, has a special importance, a special meaning in the context of this topic over here, because basically it is a map, a direct map, which tells you what you get out for whatever you get in, as a function of the frequency, of course. And then it is interesting to visualize this guy over here in a graph. Of course, it is a rational function. You can just write the expression over there. But you can also like maybe to have a visual representation, which makes things easier. And there are in the literature different choices for that. Typically Nyquist diagram or Bode diagram or Nichols diagram, also called Black-Nichols diagram. We will not look at the Nyquist diagram, we don't have the time to look into that. But we will focus on the Bode diagram first. And this Bode diagram will be key for what comes next. So what is the Bode diagram? The Bode diagram is a graphical representation of a transfer function, say, of h of s. Okay? But pay attention just a second on this. H of s is a complex function, complex valued function of a complex number. But as we realize that actually is not so important to see s for any values, because what we care of is to compute s for h for s equal to j omega. So actually we are content to visualize only h of j omega. The problem stays because h is a complex function, so basically it has a real and imaginary part, or if you wish, it has a modulus and an argument. So basically that's why the Bode diagram contains two plots. If you want to visualize h of j omega in its entirety, you need to plot the argument and the phase. So the phase is just simple. You just plot the phase as a function of omega, of the argument of h of j omega. Usually it's represented in degrees as a function of omega. The modulus is traditionally written in a strange unit called decibel, which basically is 20, the logarithm base 10 of the modulus of j omega. Don't ask me why it is like this, it's just for historical reasons. So basically, if the modulus of j omega is 1, you get log 10 of 1, 0. So basically you get 0 dB, 0 decibel. If the modulus of h of j omega is 10, you get log 10 of 10, 1, 20 decibel, etc. Every time you multiply times 10, you get plus 20 decibel. Okay, so you plot the modulus in decibel in one graph and the phase in decibel in degrees, sorry, in the other graph, then you get a Bode plot. The last trick to remember is that, considering that omega can range from very big to very small values, usually omega it is represented on a logarithmic scale. Okay, it is not on a linear scale. So basically, you don't see negative omega, which doesn't make a lot of sense. For omega going to 0, you go to the infinite on the left hand side, and for omega going to infinity, you go to the infinite to the right hand side. So let's see an example of a Bode diagram. So we said it comprises two diagrams. So this is the Bode diagram, an example of Bode diagram over here. So this is the Bode diagram of this transfer function. Okay, so as we said, there is a magnitude plot, decibel as a function of omega, angular frequency, magnitude or amplitude or gain, whatever, in decibel, and then we have a phase plot in degrees as a function of the angular frequency. Okay, so what does this mean, this graph, in practice? Let's remember what it means exactly. It means that for each slice that we take, for each omega that we take, if you input a certain sine wave at this omega, the output will be a sine wave with the same omega, but with amplitude multiplied by this term, okay, by this term in decibel, and shifted by this phase. So for example, for 10 to the power 1 omega, which means minus 1, which means the input is ut sine of 0.1 t, we get 0 dB, which you might remember corresponds to 1. You have to invert this formula. So if you have 0 over here, you divide by 20, then 0 divided by 20, take 10 to the power 0 makes 1. You have to invert this formula. So you have an amplification of 1. So if a sine of amplitude 1 goes in, a sine of amplitude 1 goes out, and a little bit of phase shift. You see what it means, phase shift? Well, the peak more or less are in the same place. Now let's take another slice. So for 10 to the power 0, so omega equal 1. Again, what is the gain? Well, we have a little bit less. Actually, we have maybe we have minus 3 dB, which corresponds to approximately 0.7. How do we compute this? You take minus 3.05 divided by 20, then 10 to the power of this gives you 0.7 approximately. So it means you have a sine at angular frequency 1 going in of amplitude 1. You will have as output a sine, same angular frequency, but amplitude of 1 times 0.7, as you can see here, and also a phase shift of 45 degrees. So you can see the peaks here are appearing a little bit later. Okay, the peaks of the output appear a little bit later with respect to the input. This is the phase shift. How later they appear? Where one cycle is 360, so they appear approximately 360 divided 45 degrees parts of cycle later. Okay, it's not so much later. Okay, you can see it here. And then let's go on, continue here. 10 to the power 1 omega. Okay, so here you see we have approximately minus 20 dB of magnitude of gain, which means 10 to the power minus 1. So if you have something going in of amplitude 1, you have more or less 1 order of magnitude of attenuation, so the signal going out will have an amplitude a little bit less than 0.1. You have the exact computation over here, and a phase shift of minus 130 degrees, which means that the peaks are really shifted away, but we don't see in this picture. So what we understand that the Bode diagram is something that you can directly use. Okay, it's something you can use directly, as we've seen before, for understanding what will be the output of a given sine input. Okay, let's define a few more concepts here. This one we have seen over here. How did I draw it? We didn't say it yet. We're going to look into that shortly. But typically, it's not uncommon to see Bode diagram like this, starting with a plateau in the magnitude plot and then going down to minus infinity. And this kind of functions like these define a notion of passband. So we call the passband the interval of frequencies for which the plateau stands, let's say. For example, the interval of frequencies until which the plateau is flat up to 3 or 6 dB of loss. So usually we can pick 3 dB, so the plateau ends where you lose 3 dB, which is approximately here. So the passband of this system is for omegas smaller than 10 to the power 0, omegas smaller than 1 radians per second. So how do we plot the Bode diagram? Well, it is just the modulus and the phase of a transfer function for s equals j omega. So if you feed it to a computer, it can do it no problem, just point by point for all omega. But there are some mnemonic rules, some practical rules, which allow us to do it a little bit more quickly. And let's start to see how it works with a simple example. So the first example we're going to see is a first order system. So h of s is k divided 1 plus tau s, typical first order system which we see. And this first order system has a Bode diagram like this. We distinguish two possible ways of plotting it. So the blue line here is the real Bode diagram, the one the computer would plot. But the mnemonic rules I'm going to tell you about rely on what we call the asymptotic Bode diagram. So basically rely on some segments of straight line that are useful to have a, say, first idea, rough idea of how the Bode diagram will behave, and then we can expect the real diagram to just be the approximation, the spline, if you wish, of these asymptotes. Okay, so basically the first order diagram, first order function has a Bode diagram starting at the log 10 of k, of modulus of k, if k is positive, well, modulus of k, and then for 1 over tau, the plateau ends for omega equal 1 over tau, and then starts to slope down at a precise negative slope. So let's now, to understand what this means, what I've written here, so let's look at the scale over here. So the frequency, the angular frequency, is written in logarithmic scale. So each space, each equal space, corresponds to an order of magnitude. So we call a decade the distance between one value and 10 times the same value. So this one, for example, is a decade. Okay, this one is a decade. So the diagram basically slopes down, the asymptotic diagram, after 1 over 2 of 20 decibel for each decade, as you can see here. For example, here we are at 0. 1 decade is this amount, you can see, and in this decade it went down of 20. Okay, so a first order system has a Bode diagram of magnitude straight at the beginning then for 1 over 2 sloping down at minus 20 dB per decade. What about the phase? The phase starts at 0 degree, then at 1 over 2 we have a step down, let's say, for the asymptotic diagram, and then it goes to minus 90. And the real diagram, of course, is just say a spline, a smoothed version of this one. So why is this so? Well, basically it's just it's very simple. The modulus of this, where s, which is j omega, is very small, correspond to k. You take 20 log 10 of k, you get this asymptote. This graph, you get 0 because k is taken 1 in this specific example, but it can be up and down. It's not always 0, it's 20 log k. When s starts to be big, then we get the denominator which grows big, so then it starts to slope down. Okay, and because we are in log scale, where this slope becomes linear in the log scale, it's a log scale, so it becomes linear. And the phase, well, the phase is the phase basically of this divided by the phase of this, which basically means we have a minus the arctangent of j omega omega and omega times tau, and basically which is this line here, omega times tau. This is the arctangent. Okay, so let's go to second order diagram. So we have to distinguish different cases. So we've seen that according to the value of psi, we have either separate real roots for the denominator, or we have complex conjugate roots. So in the case of separate real poles, which means that psi is greater than 1, then this can be rewritten as this one. And basically then we have the combination of two first order systems. So we get basically the plateau starting off, then we get at the first times constant 1 over 2 1 a first slope going down, and then a second slope going down which sums up to the first one, bringing the total slope to minus 40 dB per decade at 1 over tau 2. Okay, so basically this is the sum of what you would get if you draw a Bode diagram of k over 1 plus tau 1s and the diagram of 1 over 1 plus tau 2s. So what is interesting is that the product, because it's log scale, and the product of some terms end up giving additive term to the Bode diagram. Okay, and also for the phase it is the same, because as we said, the argument of the product of a number is the sum of the argument. Then if you have several arguments, this just sums up in the phase. So here it is the same. You get first minus 90 degrees for the first time constant, and then additional minus 90 degree for a second time constant. If we have psi equal to 1, then we have two identical roots, which means that basically the system is k over 1 plus tau s squared. And the Bode diagram basically is the, if you want, the degenerate case of this one, where these two 1 over tau 1 and 1 over tau 2 coincide. So imagine these 2 points go together, then what happens? Well, all of a sudden at 1 over tau you go from 0 slope to minus 40 decibel per decade, and also suddenly from 0 to minus 180 degrees. Okay, then if we have complex conjugate poles, which is the case for psi smaller than 1, we distinguish psi smaller than 1 but greater than 1 over the square root of 2. Well, in this case we have more or less the same diagram. There is not a big difference. So plateau, then sloping down from 0 to minus 180 degrees. Then what happens if we are between 0 and 1 over the square root of 2? Psi is between 0 and 1 over the square root of 2. Well, we have what is called a resonance. Instead of sloping down all the time, the diagram I've seen before, the diagram goes up a little bit, the real one, before joining the asymptote at the infinity. And this is what we call a resonance. And this resonance is taller if psi goes to 0. So basically psi going to 0, this peak goes up, 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 up. And you can see actually there are some formulas here you might use. So this is the gain of the resonance, which is basically the height over here with respect to the plateau, and also the angular frequency of the peak. It's not exactly omega n or 1 over tau if you wish. It is a little bit shifted off, and you can compute it with this formula. Okay, so again, remember, for psi going to 0, the peak goes up to infinity, like this. Well, so these are just two simple examples which are useful. Remember what I said, that these Bode diagrams are an input-output map for all the sine waves that you might have in. So let's pick this one again just before we go on. Imagine you have a sine wave goes in as input at this frequency. Well, 0 dB, the output will be more or less the same amplitude. Imagine you have here a sine going in, the amplitude of the output will go to infinity. So you can imagine actually the output will be a sine wave that grows and never stops. So this kind of phenomenon, if you have in a real system, is kind of dangerous. So you understand why resonance, what we call resonant peaks, are usually a phenomenon that we like to avoid. So how to draw any Bode diagram? As we said, all the terms in the products, a transfer function is the product of terms in a rational function. All the contribution of these terms sums up in the diagram, because the diagram is log scale, the decibel is a log scale, and the arguments sum up. So basically one could just separate the first order terms, the second order terms, draw the diagrams for all of them, and then sum them up. And basically there is a recipe which allows you to do this more efficiently. Otherwise, this recipe we're going to see it shortly. Otherwise, one could just take a computer or draw one by one the points that are thought to be significant and draw them in the graph. This is of course possible. So what I want to say is that the recipe, which we're going to see shortly, is not anything magic. It just comes out of some simple math consideration. But anytime you have trouble, you can always put a point in the graph just by computing the value of the function, the value of h of j omega, and computing the gain, just the modulus. Take the logarithm by 10 multiplied by 20 and write it here, and then the phase, take the argument of the number that you get. Okay, so this is what a computer will do, and you can do this in MATLAB also. So the recipe, the practical recipe for drawing a Bode plot, I'm going to explain to you now. It's probably going to sound very strange and very weird, and it will take some time to digest and to get through your your brain. So don't be scared, just let me explain to you, and then take the time to look at the examples. There are examples in the booklets, and take the time to do the exercise. And I will also show you how you can do as many exercises as you wish just by using MATLAB and drawing a diagram by hand and checking it by MATLAB. So you can do this as many times as you wish. So how does this thing work? Well, basically you have to write the transfer function as a rational function, so basically a polynomial divided by another polynomial in S, and this polynomial have to be reduced as the products of elementary components, so first order terms and second order terms, first degree and second degree. Okay, so this is the basic theorem of algebra. Every polynomial can be decomposed into these terms. Another thing that I ask you to do is to factorize all the terms, the constant terms, such that all these first and second order terms start with a 1. Okay, do not forget this. All the terms start with a 1. There is no a plus something, b plus something. No, all the terms start with 1 plus terms depending on s. 1 plus terms depending on s. And for first order term, we can just express them as time constants. and for second order term we can express them as we saw before with the canonical form of second order term, so featuring xi, the damping factor, and the natural frequency omega n, which we call here with a different name to distinguish numerator and denominator. So we define the values which make the numerator 0, so basically in this case will be minus 1 over tau zi, or the roots of this here. We define the roots of the numerator as zeros, we call them zeros. Okay? The values of s which make the numerator 0 are called 0. It's maybe an unfortunate choice of notation because we use the word for two different things, but 0 is the value of s which make the numerator 0. And then we call pole the value of s which makes the denominator 0. Okay, so once this function has been factorized in this way, okay, all terms here, the numerator, first order, second order terms start with 1, denominator same, second order, first order starting with 1. There might be some s terms which are spare, so the terms in s alone, which we factorize them all, put the denominator and call n naught the exponent which is left there, and we will have a constant, a scalar constant, negative, positive, in front of it. Okay, so the idea is to bring this function into this form, and we will see some examples. Once the function is brought into this form, the second thing that we are required to do is to compute these poles and these zeros. So compute all the values of s which make the denominator 0, and all the values of s which make the numerator 0. And then we are ready to draw the function. So each pole and each zero basically is an angular frequency. Remember that poles and zero can be positive or negative, but we will just look at the absolute value of this angular frequency. So basically for each first order pole or zero, 1 over the modulus of tau is the associated angular frequency. And for the second order terms, you can compute the roots if you want, but if you have put them there in this form, the angular frequency associated is always omega. Okay? Then we will need to look at xi to know if the real part is positive or negative. Okay? So basically for second order terms, the associated angular frequency is this omega, the angular frequency here, and the sign of the real part, which we need to know later on, depends on the sign of xi. So basically negative real part if xi is positive. Okay? Once we know all of this, basically you need to write a table with all the poles, all the zeros, associated frequency of each zero, associated frequency of each pole, and basically the sign of the real part of pole and zero, because all of them in principle they are complex. They might have a zero complex, zero imaginary part, but they have a real part, could be zero as well, and they have a sign of the real part. So again, this is written down into the booklet. You can have a look at that because of course it's not easy to understand in the first place. So how does it work? Once this table is completed, you just draw the two graphs we put the axis of the two graphs, and basically the diagrams are drawn from left to right. So from omega going to from minus infinity, from zero, say from log of omega going from minus infinity to plus infinity. So from omega going to 0 to infinity. And the idea is that you have some starting values for both modulus and phase, and then you basically sweep the graph from left to right, and each time omega has the value of a pole or a zero, the associated angular frequency of a pole or a zero, you will do something to the graph will change, and then you will continue until the next polar and next zero. So basically you start for omega going to 0. So for omega going to 0, basically there are two asymptotes that you can write. One asymptote for the gain, for the magnitude, and one asymptote for the phase. The asymptote for the modulus, for the magnitude, is basically this one over here. This one over here. How do we do it? Well, just look at this formula here. If s goes to 0, s goes to 0, s is j omega, omega going to 0, then you are left only with 1 plus 0, 1 plus 0, 1 plus 0, 1 plus 0, and 1 over s to the power n naught for s going to 0. So basically h of j omega for omega going to 0 is asymptotic to k divided by j omega to the power n naught. There you go, this one, okay? And this one, we have to draw it in the decibel, so taking the 20 log 10 of this will basically yield, by the rules of the logarithm, 20 n naught minus 20 n naught times log in base 10 of omega plus the log in base 10 of the modulus of k. Very simple. Very, very simple. Okay. So basically, if n naught is 0, you have this one alone, which means that the asymptote is horizontal. Otherwise, you have an asymptote sloping down or sloping up with a slope of minus 20 n naught. The angular frequency is in a logarithmic scale, so if you assume that this is basically the x-axis, then this is a line, this is a straight line. Minus 20 n naught times the x-axis, so this is basically a straight line with a slope of minus 20 n naught decibel per decade. What about the phase? The phase, well, is the phase of this guy over here. And the phase of this guy is basically minus 90 degrees times n naught plus a term which depends on the sign of k. So this extra term is 0 if k is positive, otherwise it's minus 180 degrees. Then, after drawing the left, say, asymptote, we said we sweep the graph from left to right, and every time we encounter a pole or a 0, we do something. And this is what we do basically when we meet a non-positive real part pole, non-positive real part, I didn't say negative, non-positive real part pole, we add minus 20 decibel per decade to the slope of the gain and minus 90 to the phase. When we have a positive real part pole, we add minus 20 decibel per decade to the gain, but plus 90 degrees to the phase. And then when we have some zeros, we do plus 20 decibel per decade to the slope in both cases, and if they are non-positive zeros, plus 90 degrees to the phase and minus 90 degrees to the phase. And if there are multiple poles or zero, like those, for example, coming from a second degree term, then the effect is multiplied by 2. Okay, if you have a double pole, then you add minus 20 dB twice. Okay, so minus 40. And these terms are added. It doesn't mean that it goes to minus 20. It adds minus 20 to the slope that you have. Now, I know this is a bit of a shock, but you don't have to learn this by heart for the moment. Just you have it written somewhere, and take it with you for now and follow the example, please, that we are going to see right now. So these are examples. This transfer function a bit complicated. We have 10 times this thing over here and this thing over here. So this is already written in the canonical form because we have all the terms in the numerator decomposed in the first order term and denominator one first order, one second order, and one s. Okay, so all the terms not depending on s have been normalized to 1 in the numerator and denominator alike. So this is the canonical form for which we are ready to start the diagram. So we draw axis, we identify the term, so this 10 is what we call k, n naught is 1 because we have 1 over s to the power n naught, so n naught is 1. I just show shortly the canonical form so you can compare it. 1 over s naught, s to the power n naught, so in this case it's 1. All terms factorized and normalized such that the constant term is 1. So let's go back to the example. So k is 10, we said, n naught is 1. Which are the poles and the zero? So remember, poles have a value and an associated angular frequency. We don't care so much for the values in themselves, we care a lot for the real part. We need to know the real part, if it is positive or negative. So let's look at the numerator first. Which are the numbers that make a numerator 0? So in this case, and these are called the zeros. So this one for s equal minus 100. So we have a negative real part 0 at 100 radian per second, and then we have 0.1, so a positive real part 0 for 0.1 radians per second. Then we have poles here. We have a pole in 0, which is already accounted for by n naught. Then we have a pole in minus 1, so at 1 radian per second. We take the modulus. This is a negative real part pole. And then we have a pole at omega n here is 10, right? It's square root of this one. So we have a double pole at 10 radians per second. Which is the sign of the real part? Well, the real part has a negative sign because psi is positive. I repeat again. The sign is negative of the real part because psi is positive. Okay? If you don't trust me, just compute the roots and look at the real part of the solution of the poles. Okay? The roots of this polynomial. So, what else we said? Then we said that we can start the graph by drawing asymptote. So the asymptote for a phase is the easiest. K is positive, so we don't have the additional term here. You remember this, the asymptote of the phase. This is 0, K is positive. Then we have minus 90 degrees time n naught, so n naught is 1, minus 90 degrees. We start with a flat asymptote in the phase at minus 90 degrees. What about the modulus? Well, the modulus is this line over here. So we have k equal 10, 20 log 10 of 10, so 20, plus minus 20 n naught, so n naught is 1, so minus 20 log 10 of omega, which is a line. So how do we draw a line? Well, it is a line sloping down 20 dB each decade, and then you can just pick a point to place the line up and down. So for example, if we take 10 to the power minus 2, then the log in base 10 is minus 2. Then we get what? We get 40 here plus 20 log 10, so plus 20. So sorry, we get 60 dB. Okay, so you fix one point and then you know the slope and you get this line. So for how long we continue this line? Well, this line will continue, this first asymptote will continue until the first polar 0, so which is the smallest polar 0 is 0.1 here, so it stops at 10 to the power minus 1. What happens at 10 to the power minus 1? We have a 0, so we look at the table here. A 0, you remember, with coming from this one with positive real part. So we are in this case. The phase goes down minus 90 more, and the slope goes up. So wow, there you go. The slope goes up from minus 20 plus 20, so becomes flat, and the phase goes down of minus 90. Until when? Until the next guy coming here. This one, a pole at 1 radians per second. This pole comes from here, so it is a negative real part pole. Negative real part pole means losing minus 90 of phase and going down 20 degrees per decade of slope, and so on. So what is next? Here we arrive at the second order term, which is here 10 to the power 1. So a double pole, which means the effect of the slope will be double, minus 40 added to the minus 20 we already had, goes to minus 60 degrees per decade. We have also the same effect twice for the phase, so we get minus 90 two times of the phase. This was a negative real part pole, so the phase goes down. Last but not least, we have this 0 over here at 100 radian per second, a negative real part 0, so the slope goes up of 20, going from minus 60 to minus 40, and the phase goes up minus 90. What about the real diagram? Well, the real diagram, we said, is the smoothed version of the asymptotic diagram with a small resonance peak here. How do we know there is a resonance peak? Well, this pole here is the double pole here. You can compute psi, and according to what we see, it is a smaller value of psi, smaller than 1 over square root of 2, and so there is a resonance peak. How tall will be this resonance peak? Well, you can figure it out with the formulas in the slide before. So again, this might be difficult to understand at first place. Please look at the examples in the booklet and try to repeat to recreate this diagram. But let me stress again, it is a very, very straightforward and mechanical procedure once you have understood it. Why we like to do this thing, by the way, because a computer can do it, so you can just in most cases do it by giving it to a computer. Well, it is nice to know actually what is the effect of each term in the transfer function, because if we know what a pole or a zero will do, we will be able to design a transfer function at a certain point. So keep this in mind. This is not just a useless exercise to do on paper something that the computer can do better, but it is interesting to understand the workings of transfer function and the working of this Bode diagram, which I remind you are input-output maps, straightforward input-output maps for signals, for systems. Okay, let's see another example. This one a little bit simpler. So actually I invite you to stop the video now and try and do this example on paper yourself, and then you can look at the solution. Solution in 3, 2, 1. Okay, so first question we have to ask, is this guy in the canonical form? Well, no, obviously no. Again, every time I ask a question, maybe I'll stop for a while to give you the time to stop the video and correct in case you made any mistakes. So of course this is not in the canonical form, because we have 0.1 here and 0.5 here. Instead we should have 1. So what we do, we divide the numerator and denominator by the same term. So divide by 0.1 and 0.1 and divide by 0.5, 0.5. And what we are left with? We are left with a k of 0.2, okay, which is basically, if you factorize this one and divide by 0.5, well, that's what you are left with. Then what is n naught? N naught is 2, because we have an s power 2 at the denominator. Then poles and 0, we have, besides the poles in 0 here, which are taken into account by n naught, we have a pole for s equal to minus 0.1 and sorry, 0 for s equals 0.1 minus sign, and the pole minus 0.5. So we have a pole at 0.5 radians per second with negative real part, and the 0 at 0.1 radians per second with negative real part. So we start on the left with asymptote, and naught is 0, so is 2, so we have minus 180 degrees here as a starting, so 2 times minus 90 makes minus 180. Then we have the asymptote is for the gain is log 10 of 0.2 times 20 plus minus 40 log 10 of omega, and it is basically this line sloping down minus 40 decibel each decade. Then this goes on until the first polar 0, which happens to be this one as 0.1. We have a negative real part 0, so phase up 90 degrees, slope up 20 dB per decade, so from minus 40 to minus 20. This goes on until the pole here, negative real part pole, phase down 90 degrees, slope down minus 20, minus 20, minus 20, minus 40. Okay, and again the real graph is the smoothed version of it. Okay, here there's not so much to smooth. Maybe here, well, the asymptotic diagram stays very little time at minus 90, so the real phase doesn't really have the time to reach it, and so it goes down like this. There is another kind of diagram which we might like to use beside the Bode diagram. Is the Black-Nichols diagram, or also Nichols diagram. And the Nichols diagram is practical because it features a single plot. So Bode diagram is 2 plots. If you get rid of omega, basically you get a single plot. So you just plot the phase against the modulus, or vice versa if you wish. So what you have is you have a more practical diagram, because there is only one figure, but you lose any info on the angular frequency. So that's why it is nice most of the time to at least identify the direction of growing angular frequency. So which is the direction of the line, in which direction it goes from 0 to plus infinity. How to draw it? Well, students always have trouble to draw Black-Nichols diagrams, and I suggest you should first draw the Bode diagram, and then it's rather easy to draw the Black-Nichols diagram. So let's have an example here. So as I said, the Nichols chart, or the Black-Nichols chart, is gain modulus against phase. Okay, so basically you take this one and put them together, and omega disappears. So how you draw it, for example, for this one here? Well, just take the asymptote on the left. On the left, this one goes to plus infinity, and this one goes to minus 90. So minus 90 plus infinity is here, up here. Okay, so then this is the starting point. So then it goes down, I see, and it goes to where? To minus infinity and minus 180, which is over here, down here. So basically, this diagram is something going from plus infinity minus 90 degree to minus infinity minus 180 degrees. Okay, if you draw it by hand, of course you don't know exactly where it will cut here unless you pay attention. For example, you want to know where it cuts at 0 dB. Well, you just read it here. You just read it here. It's not so difficult, but in general, okay, if you draw it by hand, some kind of approximation is of course implied. Let's see another example. So this is another Bode diagram of what kind of system. Do you recognize what kind of system is this one? Answer in 3, 2, 1. It is a second degree system, second order system with psi greater than 1, which means that you have 2 separate first order terms at the denominator. You have 2 real poles, if you want. And how you draw this one? Well, again, look at the asymptote on the left. Start from 0 dB and 0 phase. So basically you have a point here, 0 0, and then, well, with some ups and downs, goes to minus 180 degrees, which is here, and minus infinity down here. Another example here, you might look at this one. It's really not difficult at all. Take the time to read it if you need. And if you have a diagram like this is the case of psi greater than 0 but close to 0, then we have a little bit of resonance. So how we do this one? Well, it starts from 0 0 in this case again. It goes to, again, same as before, minus 180, minus infinity here, but it goes up a little bit in modulus, you see here, before it goes down. Okay, this is the effect of the resonance. So again, let's try and do another very simple example. Take the time to try and do it yourself, and then I think we'll see the result in the next slide. Answer in 3, 2, 1. How you do it? Well, you can draw first the Bode plot, and then you can just go from the Bode plot to the Nichols chart. Basically, it goes again from plus infinity minus 90 to minus infinity minus 180, and you can also try and compute more or less where you hit 0 dB.